Hello everyone, in this video tutorial we are going to simulate a conversion reactor using Aspen HYSYS. So this is the problem statement, and here ethylene glycol is produced by the direct hydration of ethylene oxide. So this is ethylene oxide, it reacts with the hydrogen oxide to produce ethylene glycol. The conversion is 95% based on ethylene oxide. So this ethylene glycol then reacts with the ethylene oxide to produce diethylene oxide. This is actually a side reaction, and here the conversion of ethylene oxide is 5%. The feed contains the mole ratio of ethylene oxide to water is 1 to 12. That means if I feed 100 kilomole per hour of ethylene oxide, I have to feed 1200 kilomole per hour of the water, and these are fed at a temperature of 25 degrees C and a pressure of 3 MPa. And the reactor operates at 200 degrees C, and the pressure of the reactor is 3 MPa. We are asked to use Aspen HYSYS and report the composition of the products. The heat duty if 100 kilomole per hour of ethylene oxide is processed, and the heat of reaction for both reaction if the reference temperature is 25 degrees C and reference pressure is 1.325 kPa. So open Aspen HYSYS. Double click on new. So this window is open. Now click on this add to add the components. So this is the components are water and ethylene oxide. You just need to type this as one word and no space in between ethylene and oxide, and it will search ethylene oxide. So add, and then we have to add ethylene glycol. So double click on this ethylene glycol, it will be added, and we also have to add the diethylene glycol. So just write diethylene glycol. So this is diethylene glycol. This is added here. So we have added our components. Now go to the fluid package, click on add, and go to the NRTL, and here you have to select the RPM model. So we are done with our components and also the fluid package. Now go to the reactions. Here we have to define the reactions. So click on add reaction, HYSYS conversion, add reaction, HYSYS conversion, add reaction. As we have two reactions, so I have added two reactions here. Now double click on reaction 1 and define the stoichiometry of the reaction. So we know that ethylene oxide and water, 1 mole of ethylene oxide reacts with 1 mole of water to produce 1 mole of ethylene glycol. This is 1. So the conversion is 95% in this case. You can see that this is, you can see this green line ready. That means we have provided all the specs of this reaction. Now double click on this reaction 2 and define the second reaction as well, where ethylene oxide reacts with ethylene glycol to produce diethylene glycol. So this is -1, as these are the reactants. You have to write this -1 and 1 diethylene glycol. 1 mole of diethylene glycol is produced by 1 mole of ethylene oxide and 1 mole of ethylene glycol. So the conversion in this case is 5%. You just type 5 here. Close this. Now you have to attach this to fluid package. So add to fluid package. Which fluid package? This inertial RK, which we have already defined there. Now go to simulation and click on this mixer. Okay, and add mixer here. Double click on this mixer, and we have to define the streams. So one stream is a ethylene oxide, ETO oxide, and one stream is a water. And just call this is feed 1. This will be actually feed to our heater. And now go to the worksheet. We have to define the stream. So the temperature of ethylene oxide steam is 25 degrees C. Pressure is 3 MPa, and the flow rate is 100 kilomole per hour. Similarly, temperature of water steam is 25 degrees C. Pressure is 3 MPa, and water flow rate is 1200 kilomole per hour. Now go to the composition. You have to enter the composition. So this streams ethylene oxide. It contains 100% of ethylene oxide. All other things are 0, 0, and this is 0. Okay, and now you have to define this composition of this stream. So it contains 100% water. All other things are 0, 0, and 0. And just click on this. Okay. Now the mixer is simulated. So back to the condition, and here you can see the composition of our feed 1. From here you can check the composition of the feed 1. Now let's close this, and now as the reactor operates at 200 degrees C, so we have to heat up this feed. Now just add heater from here. Go to the heat transfer, and this is the heater. So add heater here. Double click on this, and the inlet is the feed 1. The energy stream is E1. So this is E1, and just call this feed 2, which is actually feed to our reactor. Now close this. Okay, and this is our energy stream. This is the outlet of the heater. Double click on this heater, and go to the worksheet, and here we have to put the temperature as 200 degrees C, and the pressure is 3 MPa, because it has to raise the temperature to 200 degrees C. So it has calculated the required heat flow rate, which is 5009 kilowatt per hour. And sorry, this is 5009 kilowatt energy, and the required energy is 5009 kilowatt. And now we have to add the reactor. So go to the reactors, and we have to add the conversion reactor. This is conversion reactor. Click here. Now double click on this reactor, and feed 2. Just write this as product 1. We have to provide 2 product streams. Product 2. This is actually vapor product, and this will be the liquid product. I just write product 1 and product 2, and these are just the you can see these are the names of the product streams, and we have to provide 2 product streams. Now go to the reaction, click on set 1, and so this is the reaction 1, and you can also see the reaction 2. So the process is now simulated. Go to the worksheet, and here you can see the composition of the product project 2, and actually this is the condition. You can see that the flow rate product 1 and product 2. So some of the product, that means some of the product is in vapor state and some of the product is in the liquid state. And this is the composition. And now you can also check, if you click this on this direction, you can see this is, and you select the direction 1. So this is the heat of friction at 25 degrees C of reaction number 1, and you can select reaction 2 here to see the heat of reaction number 2. So this was the simulation of the problem. Thank you for watching.